My name is Ruth King, and I was the Barnett Award winner last year, so it is with absolute delight that I've been asked to chair the session this morning to introduce the Barnett Lecture for this year, who is for Mark Genton, who is a distinguished professor at the University of KAUST. And as we're starting slightly later, apologies for that, I'm not going to say anything more. I'm just going to hand straight over to Mark, get us started in this session.
Okay, can you hear me? Okay, all right. Well, thank you very much for the very kind introduction. Today I'm going to tell you the story of ExaGeoStat. ExaGeoStat is a software for Exascale Geostatistics for environmental data science. Before I do that, I would like to take this opportunity also to thank again the RSS very much. I'm very pleased and honored to receive this award. I would like to thank also the members of the statistics group at KAUST. This picture was taken last fall, and now we are more than 80. And I thank them for their support. And in particular, I would like to thank my colleagues, the core statistics faculty at KAUST. As you may know, I was privileged to go to KAUST about 11 years ago and to start a statistics department, a statistics program from scratch. So that was a very interesting experience. When I joined in 2012, then basically I was the only statistician. I had no student, no postdocs, and I was in an applied math program. And little by little, I built a statistics track in applied math and started to hire colleagues. And those colleagues, as you would say here, they are not too bad. They're actually quite brilliant. And they are listed here in order of joining KAUST. They are all a bit twisted towards environmental statistics in some way, because some work on extremes, some do Bayesian stats, or geohealth, or high-dimensional time series, and so on. So I would like to share also the award with them. I would like to take this opportunity also to thank Dr. Sameh Abdullah. He's a research scientist at the Extreme Computing Research Center in KAUST. His picture is here next to the supercomputer, and he's been a driving force to push ideas from high-performance computing linked to statistics. Okay, so I want to say just a few things also about Vic Barnett, since it's the Barnett Lecture. He was born in 1938, and actually I can relate to this very much because my own father was born in 1938. My father had his 85th birthday last month, but sadly Vic Barnett passed away earlier on his own birthday, by the way. I wanted to emphasize here these two books. The one on environmental statistics, method and application. In fact, we use this book as a textbook at KAUST in our own environmental statistics course. So this is the main reference there, and the course is being taught this fall, in fact. And also, I was very pleased to discover his book on outliers in statistical data. From my PhD thesis more than 25 years ago, I was always interested in robustness in spatial statistics, so I was very pleased to see this book, look at it, and I will talk about it a little bit later on. So that's what I plan to talk about in the lecture. There's essentially three parts. There's a first part where I will describe what I call some fundamental problems in environmental data science, and they consist in spatial Gaussian likelihood inference, spatial kriging, Gaussian random field simulations, multivariate Gaussian probabilities, and robust inference for spatial data. This type of problem becomes challenging when the number of locations where you have observation becomes larger and larger. And that was the motivation to develop this software, ExaGeoStat, to perform large-scale environmental data science. So in the second part, I will talk a little bit about high-performance computing, HPC, idea of task-based parallelism and dynamic runtime systems. I will describe tile-based linear algebra and tile-low-rank TLR linear algebra approximation. I will bring also the idea of multi and mixed precision computation in statistics in general, but also for ExaGeoStat, and then give some illustration of the software. The software we have used to run in the past 3 years competitions on spatial statistics for large data set. With the software, we are able to simulate very large data set in an exact fashion, compute exact MLEs from them and so on. And we've run a competition to test, in fact, methods that do approximation in large scale and see how well they perform. So that will be for the last part. So let me start with the first part on some of these fundamental problems in environmental data science. Of course, these problems are motivated by data, by spatial data, so data located in space, and those follow the law of geography that says that nearby things tend to be more alike than those far apart. So in the first plot here, we have satellite data about sea surface temperature on a specific day. We can have many such days. The color scheme is in degrees Celsius here. What you can see is that there are some areas that the satellite has not covered, for example here, and there are some other regions where you have cloud covers, and so you have these white areas that we would like to fill. The region is in the near South Africa, and for this particular data set here, we have about 17,000 locations. It's not too big, but it starts to become a bit large, and we have many such days that we would like to interpolate. So that's the first type of illustration. We want to learn the spatial dependent structure and do spatial interpolation. The second type of problem in this figure here is related to wind energy, and I have another big project at KAUST to study the potential of wind energy in Saudi Arabia in particular. Unfortunately, it's very difficult to have monitoring station in Saudi Arabia, so we rely on the output of climate models. Those are available, for example, like the large ensemble data set can be used. Here, what is plotted is the average wind speed for a particular time period. What you can see is that, unfortunately, the resolution is quite bad. So one pixel is about 100 kilometer by 100 kilometer. And so to infer something about wind farms, for example, we need much higher resolution. And therefore, we run a regional climate model using WRF, and this is what is plotted here on the right. So now you start, so the resolution there is 5 kilometer by 5 kilometer. The resolution is much better, of course, so you can start to see some topography, some mountain ranges, and so on. But of course, you have many more locations, so over this region, there's about 500,000 locations. So these are motivating examples, and what I would like to do next is then to talk about this problem. So the first type of problem is the following. You have n irregularly spaced observation from a Gaussian process, zero mean. You gather them in a vector z, and then you use a model for the spatial covariance function, for example, the Matern model that tells you what's the covariance between your variable of interest z at two different locations, Si and Sj, has this now familiar form, involves a Bessel function, and this is going to be the entry ij of the covariance matrix sigma. This model has 4 parameters here, a partial field sigma square, a range beta that controls how quickly the covariance goes to 0, a smoothness parameter nu that controls the smoothness of the realization of the random field, and a nugget effect tau square. Note that the variance of the process z is then sigma square plus tau square. If tau square is 0, if there's no measurement error, it's just directly sigma square. If you want to estimate this parameter by a likelihood, you can write this spatial Gaussian log likelihood here, L of the parameter theta that includes this 4 parameter here. In the Gaussian case, it has this very familiar form. It involves the log determinant and the inverse of the covariance matrix sigma. So those would typically require a Cholesky factorization of that matrix sigma that is by construction symmetric and positive definite. And this Cholesky factorization will require all the n-cube floating point operation and all the n-square memory. So you can see that when n becomes large, then this becomes a challenging problem to just evaluate this log likelihood function. Why are we interested in likelihood-based method rather than doing, for example, least square fitting on empirical variogram? Well, it's much more accurate, as we know, but here's a simple illustration, a toy example where you have an exponential covariance function which corresponds to this exponential variogram. You can think of the variogram as being just minus the covariance, if you wish. This toy example has only one parameter theta. The true value is 0.25. We simulate realization from a Gaussian process, mean zero, at 400 random location in the unit square. And then we're going to estimate this parameter theta by three methods: ordinary least square, weighted least square, or maximum likelihood in the Gaussian case. So we do this 1,000 times. So for each method, we have 1,000 estimate of the parameter theta. And of course, to those correspond a curve, the variogram curve. So we summarize this 1,000 estimated variogram curve by a box plot for function, the functional box plot. And now the area in magenta here is the center of the box. And you can see when you go from ordinary to weighted least square, you can reduce a bit this variability, but much more so once you use the likelihood, of course. So this is just a toy example. We've done many other experiments with, in fact, more parameters that interact between themselves, but that's the basic motivation to go with likelihood-based method rather than maybe the more traditional and applied least square fitting methods. A second type of problem is spatial kriging. So what we want to do is a spatial interpolation. So basically, we're looking for the best linear unbiased predictor, the BLUP, which in the Gaussian case is actually the best unbiased predictor. And to think about kriging, you can look at the following situation. So Z1, Z2 is assumed to be multivariate normal, Z1 of dimension n and Z2 of dimension m, with a certain mean vector and a certain covariance function, covariance matrix divided into the corresponding blocks. And then we know that the conditional distribution of Z2 given Z1, Z1 is what we'll have observed, again, Z1 is of dimension n location, is still multivariate normal of dimension m with a certain conditional mean in this red box here and a certain conditional variance in this red box here. So kriging is basically saying that we replace the unobserved Z2 by the conditional mean. And then you can perform uncertainty quantification with the conditional variance covariance matrix from that box. So here again, you see that when n becomes large and possibly also m, the number of new locations where you want to predict the process, then computing this quantity is going to become challenging. Now, the third problem is about simulation of Gaussian random field. So, I mean, this is very classical, but the bottom line is that, so there are two situations, unconditional and unconditional. In the unconditional case, the covariance matrix sigma comes from your favorite covariance model. It could be stationary or non-stationary. Then we need to compute also here a square root of sigma, either from the spectral decomposition or the Cholesky factorization, which is typically what we do. And then by reconstructing a z using this vector y of ID normal 0, 1, it will have the multivariate normal distribution that we want to simulate from. In the conditional case, it's the same setting as before. But now what is different is that we don't want to only compute this conditional mean and conditional variance. We want also to simulate from this multivariate normal distribution with m possibly large. And so this means that now we need also to do something with this matrix and maybe compute a Cholesky factorization of that conditional covariance matrix. Here are some simulations, some realization from a Gaussian random field with a Mattern correlation function. What you can see is that, so this is on the unit square, When you move from left to right, the process becomes smoother and smoother. And when you move from top to bottom, you move from weak, medium, and strong dependence. So for example, this case is the square exponential that is very smooth. And you see the dependence. For example, look at the red blob here. It's short-lived in space, here medium-lived, and here much longer-lived in space. So that's the type of structure that you get from this Matern model. A fourth type of problem is to look at multivariate Gaussian probabilities. So they appear in many problems, but for example, in probability Gaussian process model, and the type of application I have in mind here relates to the second type of data I had at the very beginning. I'm interested in wind farm, and so you know that the turbine have blade that will start to rotate after a certain amount of wind. And this threshold, of course, depends on the type of turbine. But for example, in Saudi Arabia, what we have in mind, there is a threshold of 4 meters per second. The region that we consider here in the northwest includes Neom, this new megacity being built, and also the first wind farm in Saudi Arabia at Dumat al-Jandal. And so you can, for each location, you have data on whether the wind speed is above this threshold or not. And then you want to do prediction at new location. And the quantity that appears there, very naturally, is this multivariate Gaussian probability that relates to the multivariate Gaussian CDF, where you have to integrate the multivariate Gaussian PDF. This integral is really n-dimensional. And this kind of object appears also in many other settings. For example, if you look at Bayesian probability regression, you may be aware of the result from Daniele Durante that he published in Biometrica in 2019. It's quite brilliant, I would say, where he noticed that if you put a Gaussian prior on the coefficient in this probability regression, the posterior actually has a closed form. And this closed form is of the so-called unified skew-normal type, or Sun distribution in brief. And that one has a PDF that is proportional to the n-dimensional Gaussian PDF times the n-dimensional Gaussian CDF. So there as well, this type of quantity occur, and also if you study excursion or contour region, there are this kind of probabilities to be computed. This will become, again, challenging when n becomes large. Finally, just a link to Vic Barnett's interest in robustness is about robust inference for spatial data. Just a few words. So most data sets will tend to have some outliers of some type. If you're not convinced, then take a look at Vic's book. The book is centered on the IID case, has a chapter on time series problem. But of course, the spatial case is even more challenging because really the position of outliers, of corrupted data, plays a role. And in fact, in my PhD thesis a long time ago, I looked at ideas such as defining a spatial breakdown points or finding the worst position of outliers that destroy estimators, or computing highly robust variogram estimators. Here, what we're considering is a case of a replicated Gaussian random field, and we use the so-called maximum LQ likelihood estimator. So what we have here, we have capital R replicate, so Zj is the jth replicate, each vector Z is of dimension n, the number of location. And then we have a function LQ, which takes the value log U if Q equal 1, so you're just back to the usual Gaussian likelihood. And if Q is between 0 and 1, it takes this form. And what this does is to bring some weight. So it's a form of weighted likelihood that will downweight unusual observations. So what you need to do also is to find the right value of Q for that. So this problem as well here, I mean, usually robustness problems are more computationally more challenging than kind of classical problems. But here in this particular case, when n the number of location and or r the number of replicate becomes large, this will be difficult to evaluate. And then you have to do it for several values of Q to find the right value of Q. So that's also a challenging problem. So these 5 problems, they revolve around the covariance matrix sigma and basically computing a Cholesky factorization of it. They are cornerstone of much more complex problems. So you may say, oh, this is just Gaussian, but this is a cornerstone to build non-Gaussian model, or to look at space and time, or to look at multivariate or multivariate space-time models. So really being able to do computation at large scale for this model is useful also for more complex models. Okay, so let me turn now to the second part here, which builds this idea of designing the software ExaGeoStat for large-scale environmental data science. So the bottom line, as I mentioned before, when n, the number of locations is large, doing exact computation of the Cholesky factorization becomes very challenging. And so ideas from high-performance computing, from HPC, can help in this case. And the software that we have developed over the past 7 years, you can download it. There's a C version at this address here, and we have also an R version for our user here. Just this remark that if, for example, n, say, equals 1,000,000, this order n to the power cube means that it is 10 to the power 18. So this is 1 billion billions floating point operations. So it's a very big number, as you can imagine. Now, ExaGeoStat is going to tackle the 5 problems that I described before, plus some extension, as I had mentioned. Of course, you may say, well, we don't need exact computation, right? We can do approximations. So in fact, the literature is full of methods that use approximation to deal with computation and memory burden. For example, you can do tapering in the likelihood, so put zeros in the covariance matrix. You can do composite likelihood. There are many other ideas that you can come up with. But the problem is that these methods are difficult to evaluate because authors, basically, they look at one data set. Maybe it's large, but not that large, but they don't really compare with other because the methods are so complex that often you don't have the package or you cannot compare too much with other methods. So the comparison are somewhat limited. So what we wanted to do is to use now this software to, in fact, propose a more fair assessment of this approximation method. And for this reason, in the past 3 years, we have organized this competition on spatial statistics for large data set with the goal exactly to evaluate approximation method on data that were generated exactly with ExaGeoStat. And because we can also evaluate the likelihood for this large data set, for example, with exact computation, we can find the true MLEs. So we can say how far approximation methods are from the true MLEs for the parameter, for instance. Or we can do exact computation for prediction and see how far approximate methods are from those. So that's the general idea. Okay, so what is high-performance computing? High-performance computing is basically the use of advanced computing techniques and technology to solve complex problems that require significant computational power. This system, typically, they're going to deliver high processing speeds, large-scale storage, so storage is also important, and high-speed data transfer. They often have multiple processors with multiple cores and also accelerators such as GPUs. The term HPC usually applies to systems that function above a teraflop. So teraflop is of the order 10 to the power 12 floating point operation per second. In this little table here, you see the different units. What we'll be interested in is the one in red, which is the exascale. So 10 to the power 18 floating point operation per second. So you may ask, do we have computer that can work at that speed, at exascale? So before answering this question, let's just talk a little bit about modern hardware architecture. Basically, you can divide them into 2 types of systems, shared memory systems and distributed memory systems. So shared memory system is a system where you have processor and cores that access a common physical memory. An example are classical x86 Intel and AMD processor or GPUs. So this is represented here. You have a common memory, and all these processors access that common memory. Distributed memory system, on the other hand, is a setting where you have multiple processors or core, and each have their own local memory, and they're going to communicate among themselves. So this is what is described here. Each processor has memory, and then they can communicate through these red arrows here. So they communicate through a network, and if this network is fast enough, then of course you can extend this to basically millions of CPU cores. The benefits of this are scalability. You can work on very big problems, reliability, because you have divided the problem in smaller tasks, and also the performance. Of course, it's more challenging to deal with, but we can go around some of these challenges. So so one more thing to say here is that in this distributed memory system, basically for either clusters or supercomputers. So this is what we're going to look at, supercomputers. So what are the supercomputers that can run at exascale? So there's a list of top 500 supercomputers. It's updated twice per year, once in June and once in November near the Supercomputing Annual Conference. You can find the list. So it's changing twice per year. And what you will find is that the top supercomputer here is at Oak Ridge National Lab, in the US. It's called Frontier. It has more than 8 million cores, and it works at 1.6 exascale, so beyond this exascale threshold. Of course, here you can read also the power. It's using a lot of energy, and I'll go back to this point a bit later about ideas of how we can reduce energy consumption, so do a more sustainable use of supercomputers. Then you have Fugaku in Japan, and you have other in Finland, in Italy, and Summit also in the US. Here are two pictures, Frontier supercomputer on the left and Fugaku on the right. These are very big machines, so it's not your smartphone that you put in your pocket. You can think about Fugaku, for example, this one, as putting 20 million of your smartphone in a single room and use this to do computation, or 300,000 standard server in that room. Of course, the cost of supercomputer is very expensive. For example, Fugaku will cost around $1 billion. So what we've been trying to do here is really to marry these two fields of statistics and HPC and define a new field that we call high-performance statistical computing. So we're just adding an S here in the middle of HPC. And the idea is that statisticians could interact with computer scientists from the field of HPC and perhaps take advantage of some developments there. And one such example is exactly the software ExaGeoStat, so to try to do geostatistics, spatial statistics at exascale. So to give you an idea of what is under ExaGeoStat, here is a brief description. So on top, you will have the type of application about climate, environment, weather, and so on. You're trying to do modeling, inference, or predictions. You will need an optimization library as well. At the core of ExaGeoStat is this idea of the Cholesky factorization operation. So how can we do this in parallel and run on this distributed system? So we need several ingredients. What we do is the covariance matrix is going to be divided into tiles. So tiles are just these submatrices here, 4 by 4 in this case. And then we're going to look at the operation here for the Cholesky factorization that we need to perform and construct the associated DAG. So this is what is done here. So you need to start with this tile here, do basically a Cholesky factorization of it. So you get this first task to do here. And then you're going to need to do a triangular solve that involves the other 3 tiles below in red. They are represented here. They depend on the tile in green, but they can be done in parallel, so they are at the same level here, and so on. So you look at the whole Cholesky factorization, and you look at the different tasks and the different dependencies, and then the DAG tells you which part can be parallelized. So that's what is here under ExaGeoStat. Now at the bottom, you have different type of CPUs or GPUs. You have systems that are either in shared memory or distributed memory, and it's going to be complicated to implement this parallelization on all these different systems, because we want ExaGeoStat to run as well on your laptop or desktop as on a cluster and on different supercomputer. So then we take advantage of what is called dynamic runtime systems. So there are 2 here, StarPU and Parsec, and what they will do is to abstract from the user this complexity of having to code with different drivers such as CUDA or MPI on different type of system, the same algorithm. It's going to find, depending on the system you run ExaGeoStat on, is going to try to find the best way to do the parallelization. So this means that the software is extremely portable. You can run it on your laptop. We have run it on all these supercomputers here. So the top 5, Frontier, Fugaku, and Summit, we have been able to run the software. I know that in the UK, there's also a supercomputer at the Met office, I believe. I don't know if it's easy to access it or not. I checked this morning, it's ranked number 91 in the list. Of course, these toys, they become old very quickly. In fact, the one that we have in Chaos, Shaheen 2, now is number 113 on the list. When it was bought in 2015, it was number 7. But we are very excited to have a new supercomputer, Shaheen 3, coming at the moment, being installed at Chaos, and this should bring us back to rank number 6 for a little bit until it becomes older again. Okay, so here are just a few more details about these different parts. Maybe I'll just say very briefly this idea of task-based parallelization, so to divide this big task of the Cholesky factorization in smaller tasks that can be run on parallel. In principle, you need to do parallel coding, and this is somewhat complex because on shared memory system you use OpenMP, but in distributed system, for example, you use MPI. So all this can be abstracted, as I mentioned before, by this dynamic runtime system. And initially, we started with StarPU, developed at INRIA in Bordeaux. And then we switched to Parsec at UTK, developed at UTK, because we have collaborator there, and it's easier to handle for us. So this dynamic runtime system, again, they will handle all the scheduling and the execution of this task in parallel. The idea of dividing the matrix in tiles and do tile-based linear algebra also is very simple. So you divide in some matrices, and you can then run this tile-based algorithm using the task-based parallelism and the runtime system on different modern HPC hardware. So up to here, there is no approximation. So you use this tile for the parallelization, but there is no approximation. You can, of course, do some type of approximation. So one type is the so-called tile-low-rank linear algebra, where essentially what you have here, if we look at this picture on the left, the lower part of the covariance matrix divided in those different tiles, they are all dense double precision. What you could do is some of these tiles, for example, below the diagonal, can be approximated. So an off-diagonal tile can be approximated by a SVD low-rank approximation. It can be different for different tiles. And then you store just some smaller matrices, and you do computation also with smaller matrices. So that's one possible type of approximation. There are some more fancy ones that we have tested, but not in ExaGeoStat, these so-called hierarchical matrices, where, in fact, the size of the tile can change. So some tiles can be divided in more subtiles and some other not. The other idea that I would like to bring here is this idea of multi and mixed precision computational statistics. So this is here particular to ExaGeoStat, but you will see that you can use it also for other problems. Most computations are done in double precision, so 64-bit. But now there's interest also to think about maybe this is not fully necessary, and you could use just single precision, 32-bit, or half precision, 16-bit, to accelerate computation and maintain an acceptable level of accuracy and save on storage. So here we can distinguish multi-precision computation, where we use a combination of different precision in different parts of the algorithm, and mixed precision computation, where you use different precision within the same algorithm operation. So this is what we're going to do here. Again, we have our covariance matrix, the lower part with different tiles. What we do is to say, well, sometimes we keep dense in double precision, the one in gray here, but some we're going to use single precision, the one in blue, and some we keep them just in half precision. How do we select those? There are different ideas to do that. What we're using is actually something that has been developed by a professor of mathematics at Manchester University, Nick Hayam, that has an algorithm to in fact do this selection of the precision required. The benefits of using this multi or mixed precision are faster computations, because you have less bit to worry about, memory savings for the same reason. Eventually you save energy because you can do things faster, and this brings scalability, so you can work on bigger problems. So we just very recently developed this R package that you can download here, but soon hopefully will come on CRAN. MMPR is an R package for multi and mixed precision computational statistics. So this is not linked to ExaGeoStat at this stage, but it allows the user, so any R user, to use the package and do computations in 3 different precision, double, single, and half, and also to do this mixed precision within this tile-based format that I have described before. And MMPR, this package, in fact, will be very fast because it's leveraging highly optimized libraries such as MKL and OpenBLAST, whereas R uses RBLAST, which is not very optimized. So in the first figure here, we're comparing the package MMPR and R, both in double precision. So here there's no lowering of the precision. And we're looking at the speed up for different operations, Cholesky factorization, matrix-matrix multiplication, triangular solve for different size of matrices. So just look at the orange, say, dimension about 15,000 by 15,000. You see the speed up of the package here, still in double precision, is almost 500 for the Cholesky factorization. Then in R, you cannot do single precision, but in MMPR, you could do single precision computations. If you do that, then you're going to have a factor of 2. So this is 1,000 times faster than doing it in R double precision. Okay, so this package, again, I mean, can be used. So you can think maybe about your own type of problem where you would like to start to bring mixed precision to lower computation and speed up computations. So now some words about ExaGeoStat, just some details. So as I had hinted before, we can save the covariance matrix or represent the covariance matrix in this tile-based format. In this row, you can lower the precision in different parts in different ways. In this row here, you can do tile rank approximation, and in fact, combining the two ideas. So this version is what Jack Dongara would say is the most responsibly reckless approach, which mixes dense and tile rank tiles and also a different type of precisions. We have an R version. It's basically an R wrapper on ExaGeoStat on the C-based version. So not much here. I mean, this is a journal cover from a recent paper that we published. I mean, what I liked is this, you have this 10 to the power 18 flops, you have the Earth spinning in the middle, and I don't know about you, but this looks very much like disco 1980s style to me. This is the timeline of the development of ExaGeoStat. Of course, this is not a small project. We started in 2017 with some very basic structure, but then we added this tile rank, this mixed precision first in band. We changed the runtime system to parsec. We introduced multivariate version as well, for example. That was the year of the first competition in 2021. The tile-centric type of mixed precision, we competed for the Gordon Bell Prize last year, and we were one of the finalists. We didn't get the prize, but we plan to compete again next year. And this year, currently, we're developing containers, some kind of docking stations, and also a C++ version of ExaGeoStat that should be more user-friendly for the user to start to modify the structure of covariances in the software. Here are some comparison of ExaGeoStatR with two existing packages, GeoR and fields. What is plotted is vertically the execution time per iteration, and horizontally the number of locations, n, up to 60,000. You see that GeoR in blue and fields, after about 20,000, we cannot run it anymore, whereas we can continue with ExaGeoStatR because of this parallelization. This is all exact computation. So the speed up of ExaGeoStatR compared to field is about 30, and compared to GeoR is about 100 times faster. This is running ExaGeoStat on distributed memory system on Shaheen 2, the supercomputer at KAUST. Again, here the dimensions are up to 250,000 locations. Depending on the number of nodes that you use, you can reduce the computation time quite a bit, of course. This is just to show off running on Fugaku in Japan on a space-time case where you can reach dimension of like 10.8 million points of the covariance matrix. This is comparing ExaGeoStatR with BigGP, which is an R package to do parallel computation for Gaussian processes. So this is for the Cholesky factorization. It's a function, again, of the number of locations up to about 100,000. This is done on a cluster that we have at KAUST with either 4 or 16 nodes. On the left for ExaGeoStatR, on the right for BigGP. What you have to notice is the scale. ExaGeoStatR here is about 100 times faster than BigGP because the parallelization is much better. This is going back to the data that I showed at the beginning that we want to fill. So we can do this very quickly for many possible days. This is done here separately, but you could also think about dependence through time. And you estimate the different parameter of the covariance model. There is also an underlying trend function. You see in the north-south direction, there is a kind of gradient of temperature. So now you can see better South Africa, the point here, and these islands here. So this is the last slide of the second part, and then I just have a few more additional comments for the third part. So this is a quite busy slide, but it's also quite interesting, I think, because it's looking at the adaptive mixed precision maps. These are presented here, and the associated reduction in power consumption on GPUs to do the Cholesky factorization. So these are the entries of the covariance matrix for different model in 2D or in 3D. This is square exponential for this one and this one. This Matern is actually for nu equals 0.5, so the exponential. What you see, you have the entry. So this is you have 200 tiles by 200 tiles. Each tile is 2,000 by 2,000. So you have of the order 400,000 entries. I mean, the value of n, the number of location here. The color represent different precision, either double for FP64, single, or let's skip the green one, or half precision. And you see, and here are the percentage of entries that were stored in this different format. So there are some interesting structure. You can see that for the smoother model, the square exponential, you need only about 1% in double precision. For the rougher model, you need about 15%. So you need more to be in double precisions. The plot below are plotting the power as a function of time for different GPUs. So each row is a different GPU, V100, A100, H100. Different matrix sizes, 61,000 and 122,000. What has been computed here, so the first column is everything in double precision, so you don't use multi or mixed precision. The next 3 rows are using mixed precision according to these different models. And what you can compute is the number of joules that have been used, and you will see that you're going to reduce this consumption here once you use mixed precision on these different models. And you can also compute per watt what kind of speed you get. So you see that you can get big speed ups if you start to store not all in double, but use different type of mixed precision based on the covariance model that you have here. So the bottom line is that this idea of using mixed precision to save computation and memory, and so to save energy, is becoming a very hot topic in HPC. And so how can we design algorithms that will reduce the very big consumption of energy from supercomputers? Okay, the last part is about this competition. I will not say too much because I already told you the idea. But the main point here is that this data set that we have created are publicly available with 1 million locations in each of them. You can download them. There is one coming up for this year's competition, and really they can serve as benchmarking data set for future research. So if someone comes up with a new approximation method and say it's fantastic, I'm willing to believe it, but I will believe it more if they run it on these data sets. We can compute the rank on the top contestant in this competition and see where it falls. If it falls above, then it's very clear. This means it's better than any of the others, and we have very clear evidence. We have, as I mentioned before, this exact computation of MLEs or lowest root mean square error that have been achieved also from different contestants, and we can really better calibrate and evaluate new proposal for dealing with large data sets. Okay, I won't go into the detail because I think I'm almost out of time. Just in this, the first competition was about Gaussian estimation and prediction. We didn't participate with ExaGeoStat. People use composite likelihood or Vecchia approximation, all different, and these are the top contestants, so they had first rank and so on. If you use ExaGeoStat for estimation, then of course you can do exact computation, so you're going to rank, rank 0. When you do prediction, if you do the prediction with the true model, then you're going also to have this rank 0. If you use the estimated parameter from this part here, then of course here there could be some small variation, so we're very close to the top team here. You see there's a big gap up to the next one, but of course you lose a little bit because you have estimated these parameters. Okay, so these slides are available from my website. If you Google my name under teaching, you will find all the slides. I included the list of all publications related to ExaGeoStat because 2/3 of them are published in HPC venues, journals or conferences, so might not be so easy to come across. They're ordered in increasing year. So this is really the first proposal here if you want to read the first version. This one here is the one for which we were finalists for the Gordon Bell Prize, if you want to read about this, this idea of mixed precision that we have used there. And finally, one of the latest is published in Envometrics. I think this is a very accessible paper for statisticians to learn a bit more about HPC and these ideas if you're not very familiar with. Okay, so just to sum up, I have described these 5 problems that all involve the covariance matrix in some form And to do exact computation would require Cholesky factorization. And we have developed the software ExaGeoStat exactly to tackle this type of problem and extensions to more complicated setting. So then I talk a little bit about ideas related to high-performance computing, this different type of parallelization. All this up to here is exact, and this type of approximation with tie-low rank or mixed precision, and some more examples about the package. This idea of using the package as a benchmark to create competition for people who are proposing approximation methods. So to finish up, I just would like to make 3 points. The first one is I encourage anyone working on large spatial data set to test your method on our benchmark data set and really look at where you fall into the ranking. For those not interested in this kind of problem, I would like to suggest that you consider looking also at our package MMPR for multi and mixed precision. I think there's a big potential in statistics to do computation in lower precisions and to gain speed and scalability by doing that. So this is an avenue that I think is worth exploring more. And several people ask me whether next year there would be a competition for 2024. I'm not sure. You know, it's a lot of work to create this data set and run the competition and so on, but we're still thinking about it. Maybe we'll do one where we introduce outliers and honor Vic Barnett on this aspect of his research. So thank you very much for your attention.
Thank you very much, Mark. We do have a range of questions. So I'm going to start off with one that says, do you see quantum computing as a possible avenue for helping with computational issues for spatial models?
Yes, sure. I think going to quantum computing is something very interesting. In fact, we started to think about this idea also and try to have, the aim to have a quantum version of ExaGeoStat. I think there's still a lot of unsolved problem and a lot of research needed. Is not an easy direction to go, but I think there is potential to explore this as well, yes.
So something you did touch on as well in your roundup, so I'm going to build on that as well, is talking about sustainability. And there's a couple of questions in relation to this. A simple one, perhaps, is what happens to these supercomputers when they become outdated? But then also, if you are having greater efficiency and saving time and energy, is that what you want to do, is to save the energy, or does it mean you will do more analysis?
Well, I think it will be both, right? Because, yeah, you save energy, so you can stop just with an analysis, but you can explore more. So, of course, this can be endless, but I think it's still very interesting. If we can think about ideas to reduce the energy consumption of computers in general, but also of supercomputers, because you see that they consume so much energy. I think that's a sustainability problem that is worth addressing. On the first question, I don't know exactly what's the use of all supercomputers. I believe they are disassembled and recycled in some way, to some extent, like our other phones and computers.
It may be interesting. Someone has done a bit of homework on this, about computing resources, and just in case this is an interesting statistic, 1 million CPU hours roughly produces the CO2 of flying between Liverpool and Istanbul and back. So whether, I don't say slightly random, but I'm sure that more interesting ones that you can come up with. But clearly there is a lot of,
yes, sure.
of this power. And then linked to that as well, is that big data arises in lots of other areas, particularly biostatistics, genomic data. And someone has suggested, have you collaborated with anyone in those areas to get a completely different perspective on these things?
Yes, actually, yes. There are some groups I've come across that use it for in biostatistics problem, this GWAS kind of work. I've seen some work in this. So yes, I think there's potential to explore this further, and there is already some work in different areas.
So I'm just going to ask a couple of specific ones relating to your talk, and then a very general question to finish off, because I am aware that there are lots of questions, but there is the coffee break coming up.
Yes.
Talking about your numerical savings, there's a question regarding whether you've looked at any bounds on the numerical error that you get when you switch between those different precisions. I can't think what they're called. Approximate and mixed precision. And also someone's asking then specifically about if you compared FP64 and FP32 to see actually what difference it makes.
Yeah, so this has to be investigated, and we've done some investigation on how much, I mean, there are two sides, right? There's the performance, I mean, how much speed you can gain and so on, but also what's the final accuracy of your solution. So we've done some experiment to see, I mean, how much you can reduce and where to reduce and experiment of this type. This has to be done also with different problems. So if you try to use this package MMPR for your own problem, you have to check in the end the accuracy of your solution and if it makes sense to use these lower precisions.
So I'm just going to ask one general question that has come in. So thinking more generally than perhaps what you were presenting today. But just find the question. So how do you see new forms of data? And they've given the example of remote sensing satellite data within the area of environmental statistics.
Well, there are many forms of data, of spatial data that we can collect, right? From satellite, from monitoring stations, output from climate model, from numerical model. They are all different type of data, but they are all spatial, or spatial temporal in some form. Then, of course, you may want to, I mean, you have different source of data, and you will need to maybe combine them or aggregate them in some way. So yes, there are many different directions that can be explored along these lines.
I suppose the question really is that what's the biggest challenge in this area with these new forms of data coming online?
Well, I think the size is always a problem. You can do some approximations, but we need to understand better, I think, what price we pay by doing different type of approximation, and this has to be, I think, evaluated on different forms of data, as were mentioned.
Thank you, Mark. If we can thank Mark again, and then we will go into the coffee break.
Thank you.